So Junehyoung Jeon is a PhD student at the University of Texas in Austin. He works on theoretical methods, including cosmological simulations and semi-analytical models to study the first supermassive black holes in the universe. His work has been focused on recent developments of the JWST observations of the earliest supermassive black holes and an unexpected population of objects called little red dots, which most of you are familiar with, proposed to be accreting supermassive black holes. And today he's going to talk us about formation and evolution of supermassive black holes in the early universe. Thank you. The floor is yours.
Thank you for the introduction. Yes, I'm Jeon. I'm a grad student at UT Austin, and it's about my work on the first supermassive black holes in the universe.
I don't think your microphone's working.
Is it not working?
Not close enough. Hey.
Okay.
Is it higher?
Can you hear me better, or no?
Very faint. Just talk louder, maybe just.
If you prefer,
There's people on Zoom.
if you prefer this one.
Can you hear me better with the mic? Okay. Yes. Okay. So the problem we're trying to address is the very massive black holes in the early universe. So for a while, this is the problem in astronomy. There have been the high redshift quasars shown in the black dots here that have been observed previous to JWST that have brought questions on how such massive objects could form so early in the universe. Of course, with new JWST observation, this problem has become more significant as JWST has observed a lot of more high redshift AGNs and at even earlier times, shown in the black and the red dots here. And it's the standard formation pathway for black holes of a massive star dying and accreting to grow to be more massive, have a hard time producing such massive objects at so early times. So to be able to produce these objects, theoretically, different, like more exotic models have come up, such as like super-Eddington accretion, where the black hole is able to grow more faster than the fiducial upper limit of Eddington accretion. Or maybe you start with a more heavy black hole seed, so that the black hole has a less challenge growing to be more massive very early on. And a second problem that arose with the JWST observation is this problem about overmassive black holes. So you have the black hole to star mass ratio shown here on the right. And locally, this ratio has been well measured. There is a well measured constraint on the scale relation between the black hole and the star mass of its host. However, many JWST observations show that such many systems were overmassive, where the black hole is relatively more massive compared to the stellar host. So that it's a question of how these overmassive systems eventually evolve down to these the local relations eventually. Of course, the one caveat is measuring these black hole and star masses at high redshift. There's still quite a large uncertainty in this measurement at high redshift, but trusting these observations for now, there seems to be this issue of overmassive black holes as well. And lastly, there's of course this new class of objects named the little red dots. It's unclear what they are currently, but a more popular theory today is that they are accreting AGN that's embedded in dense gas. So in this talk, I won't talk too much about the little red dots, but tomorrow at the lunch talk, I'll talk more about my work regarding the little red dots. For now, I'll focus on the general supermassive black hole population in the early universe. So to study the formation and evolution of these first supermassive black holes, I use theoretical models. So to start with, I use cosmological simulations. So this is a movie from one of the simulations I've run. And through these simulations, we're able to realistically model the cosmological environment of black hole formation and their evolution. And in these simulations, I consider two formation pathways mentioned earlier for black holes: the stellar remnants and the heavy seeds from direct collapse. So the stellar remnants we're all familiar with, where a massive star dies and leaves behind a massive black hole remnant. And for the first early universe, we consider top 3 remnants, or the first mellow-free stars. And these mellow-free stars are expected to be more massive than the stars today in the local universe. So they are generally able to form more massive black hole seeds, so around like 100 solar masses or so. So that's more massive than what's seen locally, but still very low relative to the quasars and the AGNs we see at high redshift. The second pathway is the heavy seas from direct collapse, where you have a giant gas cloud that collapses directly into a massive black hole seed and is able to form a more massive black hole around 10 to the 5 solar masses. So it is able to have an easier time reaching the high masses that has been observed. I will go more into details of the conditions for direct collapse later on, but to start with the star remnant seed, we have in our simulation top 3 star formation, and then which live behind black hole remnant seeds as they die. But unfortunately, we have a hard time growing such remnant seeds. So on the left plot, we're here show the mass evolution from one of the seeds in our simulation. And we'll see that compared to the theoretical Eddington rate, our black holes don't grow at all. They stay very dormant, staying almost not growing at all throughout the cosmic history. The reason for that is that the black holes have a hard time accreting, so that these stellar remnant black holes are born in environments where there's already a stellar population. So a stellar population needs to form before a stellar remnant can be born. And in these star-rich environments, the stellar feedback heats up the gas. The right plot here shows a gas density temperature phase plot near the black hole, and then you see that most of the gas is a 10 to the 4 Kelvin stellar feedback heated phase. So the black hole, the low mass black hole, has a hard time accreting such hot gas. And even without feedback, a second problem is that the black hole doesn't stay in place. So the low mass black hole can wander around the central region of the halo. And where there's a dense gas region here, the black hole doesn't really stay in that region. So even without stellar feedback, the black hole does not have to stay in this dense region and is not able to accrete the dense gas available and grow very slowly. So because of these effects and slow growth, we expect that these black holes to not be able to be observable even without JWST. So here in the solid lines are the predicted fluxes from some of our simulated star remnants. And then compared to the JWST limit on top here at 2 microns, you see that all of our sources are very order of magnitude below the detection limit. But to be able to observe these black holes, you need to be more optimistic. You have to assume that they are able to grow at Eddington one way or another. Already a heavy seed direct collapse black hole can do it. So the direct collapse black hole pathway is the second method we examine in our simulations. And then I'll briefly go over the scenario for direct collapse, is that we have a dense particle that does not cool efficiently and is able to collapse directly into a black hole. So we have some chemical criteria for such collapse. So we impose that the gas has to have low molecular hydrogen fraction, low metallicity, and temperatures that's not too high or not too cold. So all these chemical conditions require that the gas particle does not cool efficiently at low temperatures. Because if the gas particle is allowed to cool, then it will instead fragment to form stars instead. But by having these conditions, we impose that we model the conditions that the gas particle can isothermally collapse into a direct collapse black hole instead of multiple stars. Of course, there are other theories of direct collapse that are out there, such as the gas cloud could first collapse into a massive star and then into a direct collapse black hole. Or maybe it forms a dense stellar cluster that hierarchically merges into a more heavy seed. Of course, we consider the first scenario here, but all these other scenarios can also produce such a massive seed in the universe, or have theoretically proposed to produce massive black hole seeds. And of course, and the one limitation of our simulation is the resolution. So we can't actually resolve the physics of black hole accretion because this order of magnitude and scales is quite different. So we have to use some subgrid model of black hole accretion. And then here, because we want to test optimistic accretion to see what the most optimistic thing that the universe can produce, we impose a gas environment condition for black hole accretion. So we consider the fueling of the black hole through the nearby gas environment, so that in our accretion model, the black hole accretes the gas from the nearby gas particle, so that if the black hole resides in a dense gas environment, it'll be able to efficiently accrete that gas to become a massive black hole. But if the black hole resides in the low density gas region, then it won't have enough fuel to accrete, and then in turn, it will result in a more inefficient growth and lower mass. So we run our simulations and produce some multiple direct collapse black hole candidates. Here are 4 cases from our simulations. And then in comparison with their stellar masses. So even here you see that we are able to produce overmassive systems. And then in post-processing, we see our black hole accretion And then we find that we have designed them to match the Eddington rate in the orange line. So the blue, like up and like intermittent curves are actual accretion rates from the simulations, which have been designed to match the Eddington rate as long as the gas environment will have allowed them to. So if the black hole is able to fuel itself with the gas around it, it'll be able to grow efficiently, but otherwise it will not be able to accrete very efficiently. We then go on to examine what kind of environment are to support such high efficient black hole growth. Only first order, we find that the overall dark matter halo environment doesn't necessarily correlate with the black hole growth. So I show two cases here, cases A and C. And case A here is an order of magnitude higher halo mass, the halo gas mass than the case C here. But you see that the black hole growth is actually more efficient than case C compared to the case A. So while the halo in case A on the left has more fuel available, not all that gas goes down to the black hole to be accreted at. What's more important then is the black hole, the nearby gas environment near the black hole. So here I show the gas velocity phase plots. And cases C and B on top are cases where show more efficient accretion than cases A and D on the bottom. And you generally see that cases C and B, the black holes reside in a more denser gas environment. There's case A, where you see the gas, maybe harder to see, but the gas is streaming across the black hole, or case D, where there's too few gas particles nearby. So rather than the overall halo environment, it's a local gas environment that affects is able to support such efficient growth better. And we compare our simulation outputs against observations. And then the solid line here are the black hole mass evolution from our simulations. And we are able to produce many of the JWST observed high redshift AGNs, and they're very extreme masses at high redshifts. Of course, we still have a difficult time reaching the most massive quasar. So maybe for the most extreme objects, we may need super-Eddington accretions on top of heavy direct class black holes to reach the most extreme cases. Of course, and then we are also able to produce overmassive systems that have been observed in early times, even the most extreme objects. Of course, one limitation is that these systems don't evolve down to more like less overmassive systems over time. They stay overmassive. And we believe that's the limitation of our box size. So because our simulation has a finite box size due to computational cost, structure formation is not as efficient as cosmic evolution happens at lower redshifts. So maybe if we read that our simulation larger volume, it'd be such, you see in case D here, there's like a merger event that significantly brings down the ratio quickly. Maybe such merger events with other systems would be more common, which will eventually bring down these overmassive systems to the more low correlations over time. And then we do some initial like rough spectral modeling, and we find that our objects are expected to be observed with the JWST as the AGN spectra are bright enough above the JWST observable limits. So this is consistent with that we have observed such systems at such early times, even at redshift 10 or so. Of course, with our simulation, we only show individual objects and show that the most extreme scenario of how heavy seed accreting efficiently could produce these extreme objects that have been observed. But we still have never really observed a heavy seed directly, a direct class black hole directly, and we don't know whether the universe actually produces them or not. So to distinguish what the actual overall scenario of black hole formation evolution might be, we could try and go to examine the overall black hole population. So this is the broadline AGN mass function at high redshift that has been observed recently with the JWST. And then what we have done is try to model this overall Supermassive black hole population and then see what different scenarios of black hole seeding, heavy seed, light seed, and accretion, such as Eddington or Prevalent accretion, might produce such different populations at high redshifts, so that maybe future observation or what kind of observation signature in the future may help us distinguish the evolution scenario from the black holes. Of course, modeling the whole population of black holes through simulation is very difficult, as you will need very large volumes, which are very computationally costly. So instead of simulations, we turn to semi-analytical models, which are more computationally less costly, but still able to model a large population of black holes. And we specifically use the A-SLOTH semi-analytical model, which have been calibrated at high redshift and includes POP3 star formation. And on top of A-SLOTH, I built a black hole formation evolution models, including heavy direct class black holes and star remnants. And then we just run these SAM models for multiple scenarios and see what differences arise. So here we show our mass function results. So we test the heavy seed models into the light seed only models. And we find that both models is able to well reproduce the observed black hole mass function at high redshifts. Of course, the one main difference with heavy seeds is this peak shown at the canonical heavy seeding mass around 10 to the 5. But besides that, at the current observable regime, there doesn't seem to be much distinguishing factor of these scenarios. The top green line here is an extreme case where we impose that every black hole is accreting a super-Eddington. So of course that enforces, that overproduces a black hole. But well, the reason we include this is when you go to higher redshifts, some differences do occur. So this is our model black hole mass function redshift 9 to 10. And these are upper limits, but they're not very strong constraints because these are just individual objects. So they're just one object. So I just do that 1 divided by their approximate survey volume to get these upper limits. So depending what future observations bring, these upper limits could go up or down. But what we find is that the stellar remnants, shown in the purple region here, cannot become such high mass object at high redshifts. You either need heavy seeds here, or you have to force super-Eddington accretion into these light seeds to be able to reach such high masses. So maybe we could say something about the black hole seeding case, but still, unless we rule out heavy seeds or super-Eddington accretion, so both light seeds or heavy direct class black hole seeds can reproduce the currently existing observations. Of course, the real universe, probably not everything is accreting as super-Eddington. Probably only a very small fraction of objects are able to accrete very efficiently. So we combine our models to have our general model combined against a very small fraction of efficiently accreting black holes. And then we're still able to well reproduce observations. And then we compare our model against the observational predictions of what the future JWST surveys could observe. So in the vertical lines here are the lowest mass black hole that predicted for different JWST surveys to identify. And unfortunately, what we find is that even the future deep field surveys with JWST will not be able to go down to this significant difference at the peak at 10 to the 5 solar masses. So it'll be still hard to distinguish what the actual formation scenario of the first black holes are. Of course, we predict that if we have some exotic scenarios, there's gravitational lensing. So this black line is a prediction for the lowest mass black hole that a gravitational lensing survey with the JWST could observe. We could go down to these low black hole masses and maybe actually observe this peak here. Of course, a few caveats is that gravitational lensing surveys probe such as much smaller volumes. But if this peak exists, maybe there are more abundant number of heavy seeds, it might be easier to observe. Another caveat is that this peak height is not well constrained. So the actual conditions for a direct class black hole is not too concrete. So if we change the conditions a little bit, we're able to change its peak height as well significantly, as seen in the gray line here. Of course, this peak should exist no matter what, as we predict, should heavy seed actually form the universe. So maybe in the near future, gravitational lensing surveys will be able to probe down to this low mass black hole regime. And if they do detect such a peak in the mass function, we may be able to actually detect direct class black holes in the nearby future. We could again go to higher redshift, right, redshift 9 to 10. And again, unfortunately, there isn't too much difference at this early redshifts. What we propose we can constrain is this fraction of highly accreting black holes. So here is there's not too much constraints about mass function. I test different percentages of like small fraction of the super-Eddington black holes. And you see that based on this fraction, the amplitude of the black mass function changes significantly. So if a universe allows for high efficient accretion of the black holes, they should become observable as they're the most extreme objects. And that will have a significant impact on what is height of the mass function is at the earliest times. So with future observation, we may be able to constrain this height, which in turn may tell us what the fraction of these very efficient or much bright objects are, maybe, and then in turn we'll be able to tell what kind of environments are able to support such extreme growths. And then on the last slide, say some maybe other characteristics. This is the black hole to stellar mass relation again. And then the light seed case here, stellar remnants here, and the direct class black holes here. And the difference is, of course, the direct class black hole much more easily produces this overmassive system compared to light seeds, as they form very massive early on. And then able to more easily produce these observations with the JWST. Of course, if we impose super-Eddington accretion onto the light seeds, the light stellar remnants can also produce this overmassive systems. But still, the one key difference is at the earliest times, the light seeds cannot be overmassive as they start with much lower masses. So maybe if we are able to probe this ratio at the earliest times, which probably is very difficult even now with the JWST, we're able to detect the signatures of direct collapse should they exist in the universe. And the last, under a different criteria, the metallicity. So this is a metallicity black hole to star-mass ratio plot. And then we expect, because we expect the direct collapse black holes to form in pristine environments, if we're able to detect overmassive black holes in pristine conditions, they might indicate, they might favor a direct collapse black hole scenario rather than a star remnant, where they form in a stellar population, so thus their environments are more metal enriched. So I'll leave my conclusion slide here, where through our simulation, we show that biased regions of the universe under the optimistic scenarios of heavy seas and efficient accretion are able to produce these most extreme objects. And that we may be able to prove the existence of such extreme objects through future population object observations with the JWST of more high redshift black holes. Thank you.
Okay, do you have any questions? Okay.
Very interesting talk. So I have two questions. In your slides where you showed the simulated direct collapse black holes. And then I was wondering why so some of these cases,
Yeah.
redshift 15 or whatever that redshift is, the initial black hole mass is very, very high. So
yes.
we start for like the
Yeah.
green line.
Yes,
like it's 3-4 times. So the initial mass, black hole mass, the form, is it like 3-4 times 10 to the 6 or something?
It is around 10 to 5, but then soon after formation, it swallows all the gas that's nearby, because it's already in a dense region. They're seeded stochastically, so like 15, between 15 and 10, I believe, for these cases. Yeah.
Like what limits you to stop the simulation at redshift 5? So can you just go over redshift, or
we can, but it'll be more expensive, so we just stopped it at 5 for now.
So as we currently understand dark matter, you're not going to get a lot of dark matter into these black holes, but there's an awful lot of dark matter. And I'm wondering if, since we don't know much about dark matter, there's some property of it that you could imagine that might cause large amounts of dark matter to form a black hole early on. I mean, is anybody about? That's a dumb idea.
I think some people have thought it, but at least in the standard like cold dark matter case, it's very difficult because dark matter will like viralize as it collapses, and it's hard to bring it down to the actual scale of the black hole accretion, which is quite small even compared to the halo scale. Like I think people have considered like self-interacting dark matter, which will have an easier time collapsing, so maybe they could form black holes or be accreted onto the black holes. But yeah, at least in the standard CDM case, I think it's very difficult to do so.
Then maybe, maybe regions of dark matter could have, a charge, for example, and so you get a somewhat charged black hole that would be then sometimes surrounded by other dark matter with an opposite charge, something like that. I don't know. It just seems like these mechanisms are not quite enough yet.
This is a fun bit of work you've done. One question I have is when you're showing the limits on JWST detectability.
Yeah.
Obviously JW has the bigger mirror, but Euclid and Roman are going to vastly beat it in terms of area covered. Do you have any perspective on what they will be able to constrain for this problem?
Yeah, I guess they'll be able to observe like the most brightest objects. So maybe considering this amplitude of the mass function, that's what I've been thinking about. Because I guess these are like the lower mass limits, but if you're able to if they're like bright object duration 9 to 10, Euclid or like large scale surveys will define them most likely. So I think it sort of strong constraint on what the number density of the brightest objects are, which could then in turn like sort of constrain on how many objects are able to accrete very efficiently at early times.
Thank you. Any more questions from me? I see no. I can see online, and I think there are no more questions. We're just running out of time. Thanks for Thanks, both speakers, and see you next time.